Hi guys, good morning. First, I would like to make a roll call. We have here James Provizzo, Rename Tondo. Do you hear me? Is my audio clear? Thanks. Um, so we have here James Provizzo, Rename, Era, Eugene, Jezreel, Ariane, Anafe, Joven, Steve, Melba Grace. We also have David Paul, Jerome. Who else are here? Marsden, Michael John, Laika Jen. We have also Liza May, um, GJ is also here. Mm, those are probably the people here. So anyway, in today's lecture, I'm not going to give a review of the previous lecture because I realized that you can review the previous lectures with um, by watching again the previous lecture. So we will start directly with the the lecture without reviewing the previous ones. By the way, I plan to have a interaction session with you, maybe using Zoom or Google Meet. But that would be in chapter 2 because we'll be solving electrostatics problems. Here, this chapter 1, will just be mathematical introductions. So these are just things that you already know, but I'm just giving you a review of it. So in chapter 2, we'll be doing some interaction session after the YouTube live class. We will proceed with like 10 to 20 minutes of interaction using Google Meet or Zoom. So for this lecture, again, our main reference is Introduction to Electrodynamics by David J. Griffiths. And yeah, uh, if you can, please buy this book. So we had the del, we discussed that before, and um, del is the generalized derivative, and the del, this one, um, the del is a vector operator. It's an operator because it's not an ordinary function, or it's not an ordinary number. It's a generalized derivative, so it acts on a function. Like t is a function. T can be any function. It can also be a constant, but in general, t is a function. So um, it operates on t. So um, as a generalized derivative, the del is composed of derivatives with respect to the coordinates like x, y, and z in the Cartesian coordinate system, or in other coordinate systems like spherical coordinate systems or cylindrical coordinate systems. It could look different, but the essence is still the same. It's still the generalized derivative. So, by the way, you can apply the del twice. you can apply it twice and get a second order derivative. And by the way, there's this is this expression here, del of t, is the gradient of t. No, so you can also, because this is a vector, you can also get the divergence and curl of this, the divergence and the curl of this gradient of t. So anyway, you can use the del in getting the divergence of a gradient. So here's the expression of that. This is the divergence of a gradient. Divergence of a gradient. So this is the form of the divergence. This is the gradient. And you can simplify it into del square of t. This is also the curl of a gradient. The curl of a gradient. And this is the gradient of a divergence. This one is a divergence. And the divergence is, this one is a vector. And this one is also a vector. V is also a vector. So the divergence of a vector is a scalar. Or the dot product is always a scalar, no? So, or a scalar function, for example. So if you apply del to a scalar, then that's a gradient of that scalar function. This is also valid. This expression is also valid. This is the divergence of a curve. This one is a curve. And you can dot, this is a vector, so you can dot a vector to another vector here. So this is the special name. It's called divergence of a curve. This one is a curl of a curl. So this is curl, and then you curl the curl. So those are valid expressions. Let's look at the first one. So you have the divergence of a gradient. Here, of course, this one is equivalent to this, this. So that is the expression for the del. Remember that this is the direction of the derivative with respect to x. This is in Cartesian coordinates. It looks different for spherical coordinates and cylindrical coordinates. And by the way, as I always remind, the x, y, and z are unit vectors along the x axis, y axis, and z axis respectively. The direction of x hat is constant. It's always in one direction. The negative x hat would be in the opposite direction. This is constant in direction. This is also constant in direction. And the magnitude of each one of these unit vectors is equal to 1, meaning those unit vectors, x hat, y hat, and z hat, are constant. They don't change in magnitude and they don't change in directions. So those are constant vectors and unit vectors. And this unit vectors is only constant for, or the unit vectors for the Cartesian coordinates are constants. In other coordinate system, the unit vectors are not constant. Only in the Cartesian coordinate system. So this one, your gradient of t is this one here. So you are distributing t to the derivatives. So when you do this, you can simplify this. You can dot, you can dot you can dot this component with this, and then you can dot with that, and here you can also dot with this, and you will get this expression. You'll be able to get it. So that's how simple it is. as you can look at it. So you know how that product works. So just review the previous lectures, and then you'll be able um, to manipulate this. This is called the Laplacian of t. The second generalized derivative of t is second order generalized derivative of t is called the Laplacian of t. The Laplacian is a scalar quantity. The Laplacian of a scalar is a scalar quantity, I mean. There's also Laplacian of vectors, or Laplacian of a vector function here. You can. So in this case, your Laplacian has direction. In this case, your Laplacian, um, there's no direction at all. There's no direction. You cannot see any direction here. This is purely a scalar function. I mean the sum. Here, there's a Laplacian of a vector. In this case, um, you're applying del square to v, and v has components. So your Laplacian of a vector function will look like this. You have in the x direction, in the y direction, and in the z direction. And in the case of the x direction, you have the component of x, which is vx. The component of vx along the x hat is vx, and you can get the Laplacian of that because the component here vx is a scalar function, and so they can get the Laplacian of that. So each of the components you can get the Laplacian, and if in doing so you will be able to get the generalized second order derivative of a vector function v. So here it is. So I hope you're not confused with this and this. Okay. So they look different, but this one will just be for one component here. And for the next component, and for the... Now we go to the curl of a gradient is always 0. The curl of a gradient, because this one has the same direction as the gradient of t. The del has the same direction as the gradient of t. So it's 0. So as I've told you earlier, the x hat, y hat, and z hat are constants. And also in Cartesian coordinates, you can do this. The commutation of derivatives. So you can get the derivative first of t with respect to y, then you get the derivative with respect to x, or it can be, or you can do it like if you get the derivative with respect to x first, then getting the derivative with respect to y. So there's no difference. They are commutative, meaning you can interchange the derivatives in Cartesian coordinates in general. So here, using the Backup rule, you can also get the expression for the curl of curls. So you can simplify this term into an expression without a cross operation. So in this case, your cross products does not appear anymore on this side. So, and by the way, this one will just be that one. This one, and each of these one will just be this one. So yeah, don't confuse yourselves. Now we go to some operations which are also very common in electrodynamics problems. We uh, do line integrals, surface integrals, and volume integrals. And this is part of the integral calculus that we'll be using when we solve electrodynamics problems. So um, so again, yeah, line integrals, surface integrals, and volume integrals. We do the do those things commonly or usually in solving electrodynamic problems. So first of the integrals is the line integral, which looks like this. In your ordinary calculus or in your calculus course, ordinarily you don't uh, do this, but you're actually doing it in a different manner by doing integrals of multiple variables. But this one here, in our case, will be doing line integrals, and this integrals involves expressions of vectors inside the integration or in integral sign. So here is a vector dotted to a infinitesimal variable dl. So there's a dot product. So in this case, what is the expression inside? This is a scalar inside. So this is the general form of the line integral. So v is a vector function. So you can put a vector function. In ordinary integration, you can just have v as a one component function. Then you just integrate it with dx or dy or dz. But in general, this is what it looks like: a vector dotted to an infinitesimal displacement vector. So dl is the infinitesimal displacement vector. So for line integrals, it looks like you're integrating through a path. We will do an example using paths in integration. So let's go further. But if your path is a closed path, for example, if A is here, and then you integrate to a point B, and then you get back to the original position. So you're integrating from A to B to A, then you are integrating in a closed loop or closed path. This means that your final position is equal to your initial position. So your integration will look like this. It has a circle. It has a circle here. This means that you're integrating over a closed path or a closed loop. So this one is just an integral using a path P, which is not necessarily a closed loop. But if you know if it's a closed loop, you have to put a circle here. You have to put a circle here. So A would just be a uh, is a point with three coordinates, and your B is also a point with three coordinates. So this is from A to B. In ordinarily, this will just be a number and also a number in ordinary integration, but we're now generalizing the integration. So in maybe some time before, you have already have done this kind of integral. The work is just the integral of f dot dl in your work energy theorem topic in maybe some in one of your physics subjects before. Um, so here's an example. By the way, class, you can write this to be able to understand the examples. You can write this example by hand, the solution, so that you will know how to solve, and you will retain some of the information in your brain. You can rewrite this by hand. Although I'm going to present this, but in order for you to really learn and retain some information in your brain, you can rewrite this during replays, or now you can write it also. So example, calculate the line integral of a function, uh, of a vector function. This is a vector function. So you have two components of a vector function, y squared x hat, 2x times y plus 1 y hat, from point 110 to the point 220. So you have here paths. One path is this path. It's like two segments. One segment is horizontal, and the other segment is vertical. That's for path one. And for you can also um, choose another path, path 2. So here you have from A to B. So the question is, what is the integral of v dot dl, the line integral? First, we have to solve from A to B, and then I mean along path 1, and then we solve with path 2 control. So this is the figure. So remember, this is a given vector function. So let's look at that. Um, Here in the Cartesian coordinates, no matter what you, no matter if the problem is two-dimensional or three-dimensional or just one-dimensional, you should always write dl as um, this expression. So dl is just dx x hat, dy y hat, and dz z hat. In this case, for path 1, it contains two segments or two parts. This is part 1, and this is the second segment. So along the horizontal segment here, this one, what is dy? What is the value of y here? So the value of y in this horizontal segment is constant, and the value is equal to 1. The value of y is equal to 1 here in this segment. In this segment, the value of y is not constant. It changes from 1 to 1.5 to 2 and so on. So it has many values here. Only x is constant here. In this case, only y is constant, and then your x is changing from 1 to 2. Here, your x is constant, which has a value 2, and then your y is changing from 1 to 2. So let's look at this. look at that. So dl is equal to what? Your y is equal to 1. So if you get the derivative of y, that's a constant. Y is equal to 1. So the derivative of y would just be the derivative of 1, which is 0. So this one is 0. And of course, this is two-dimensional. You should set this as 0 also, because we're just dealing with x and y coordinate system. So the dz is constant. So it's 0. And the value of the dz is 0, and the derivative of 0 is 0. So dz is 0. So along the horizontal segment, dy and dz is equal to 0. So your dl will just be dx x hat. So it has a direction x hat. Okay. And of course, your y is equal to 1. Your v that dl will be, so what is your, this is just the x, dx x hat. So your 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 v will just be dotted with dx x hat. So this will just be y squared dx. This one, dy is equal to 0. So if you dot dy y hat to this, everything would be 0. So your v dot dl will just be equal to this one. So now I integrate that, integrating v dot dl from 1 to 2. So v, um, y square here is, y is equal to 1. So 1 square is just equal to 1. So this is just 1 here, 1. So that's just the integral of 1 times dx, or dx integral from 1 to 2. So if you integrate this is just x evaluated from 1 to 2. So 2 minus 1 is just equal to 1. So that's for this part, for the horizontal part. How about for the vertical part? This one, um, for the vertical part. So of course here x is equal to 2 in this part. X is equal to 2. So derivative of x is equal to the derivative of 2. So dx is equal to 0 because 2 is a constant. Z is of course 0. So here dl is now equal to y hat for this segment. So this one is 0, this one is 0. So you're only left with this part of the dl. So here you have that. And then b dot dl for the vertical path will just be 2x plus 2x times y plus 1. That's here, because you're only dotting this with dy y hat. And of course, this will be dotted to 0. So it will vanish from the v dot dl. So you only have this one. Now, x is equal to 2 for the vertical path. X is equal to 2 here. So you can replace this with 2. So 2 times 2 equals 4 plus y1 dy. So your line integral would now look like this. So 4 can be taken out of the integral. So you're just integrating y plus 1. So the integral of this is y square over 2 plus y, evaluated from 1 to 2, and then you will get 10. And so therefore, uh, your integral from a to b is now equal to the sum of the horizontal path, this one for the horizontal, which is 1, and for the vertical segment, which is 10 here. So the total line integral from A to B. A to B is again point 110. This is the limit for, so z is 0 here. Z is 0. Z is 0. So x a is 1 and xb is 2. Ya is 1 and yb is 2. That's why your limits here, your limits for the x is 1 to 2, because this is xa and xb, and this one is ya and yb. So you have here the the um, integral from a to b, the line integral. So that's the generalized form of integration that you have done before this one. So for path 2, in this case, looking at this figure, path 2 is from A to B. Look, this is a diagonal line. So this means that your x and your y is not a constant in this path. No, it's not a constant in this path. The value of x here is 1 and the value of y is 1. But here it would be, they would change as you go up to b. Mhm. So looking at that, your dx, so here, your dx is, so by the way, if you look at this, look, x is equal to 1 here and y is equal to 1. Therefore, x is equal to y here. At this point, the x would be here, and also the y would be here. So they will have the same value as well at this point. And at this point, they also will have the same value. Up to this point, the x would be 2, and y is also 2. So the expression for this curve or line segment would be um, x equals y. That represents this line, x is equal to y. So if you get the derivative of x, that's just equal to the derivative of y here. So of course, z is always 0 in this problem. Z is always equal to 0. So therefore, your DL would be this expression. This expression. So v dot DL would now be what? So this is y square that y square x hat dot dx x hat. So this is y square dx, and this one is also 2x y plus 1 y hat dot dy y hat. So this would be just 2x times 1 y plus 1 dy. So here, here. So but x and y are equal. So you can write the y square into x square, because y and x are equal. And here, of course, y and x are equal. So the y here, you can write as x also if you replace, do the replacement here. So everything will be reduced to this expression, because also the dy here is replaced by dx because they're equal. The dy is equal to dx. So everything you can. So it's now a very simple integration with one variable. Or you can also do things in another way. You can also change, instead of changing y square here, you can change dx into dy. So you have y square dy. And And also you can change 2 times y instead of x times y plus 1 dy. So you can do the integration. It will just give you the same result. But anyway, let's just look at the x here. So now you will have the integral of x squared plus 2x dx will just be x cubed plus x squared evaluated from 1 to 2. So you will have 10. You will have 10. So in this case, what can you say? Using a different path. This one is a different path. This is the path used in that integration, this one. But this path is the diagonal path. This is the diagonal path going from A to B. Going from A to B. So they give different results. In general, they give. But sometimes they give the same result when the vector here is conservative. When the vector is conservative. The v vector function here is conservative. But if it's not conservative, they're not equal. So in this case, by the way, you're going from A to B. You're integrating from A to B. This means that you're going from here to here, and you got 10. But if you go from B to A, if you change the limits, if you interchange the limits here, if this is B to A, this would be negative 10. The change of the result will change. The sign of the result will change. And also here, if you interchange A with B, this will just give you negative 11. So it depends also on the direction of the path. So how about getting the closed integral, meaning you close the path. So in this case, you have, for example, you go from here to here, you get 11. You get 11. But here, from A to B, you get positive 10. But if you go from B to A, if you go from from B to A, that would be negative 10. So for the whole path, that is 11 minus 10. For the whole path, you will have this 11 minus 10, because using path 1, it's 11, and for the other path, it's negative 10, going in the opposite direction. So this is 1 for the closed loop. Now you are integrating for a closed loop. Closed loop. That is now, what is that? What does it mean? 1 is the area. 1 is the area here. The area inside the loop. That is the area inside the loop. So that's it. So that's for a line integral. Then we go to the surface integral. The form of the surface integral is, the generalized form is this one. You're integrating over a surface. This means that your dA here is an infinitesimal patch of area. dA is an infinitesimal patch of area. V is again a vector function. So that is the form. And you're integrating over a surface, not anymore a point. The line integral is very simple, but here the surface integral is involving an area, a patch of area. That means, what is a patch of area? You have a patch of area that looks like this. Um, so if it's three-dimensional, you have a patch of area with directions x, y, and z. So in this case, look, you have an area here, and the patch is directed perpendicular to the area. The direction of dA is perpendicular to the patch in this figure. It's always perpendicular. So if your area is here, if your patch of area is here, then your dA would be directed, your dA would be in this direction. That is perpendicular to the patch of area. This one is your patch. This is your orientation of the patch. So your dA would be in this direction, in that direction. And for this patch, your dA would be in this direction. So for a patch, they are going different directions for a different patch. So anyway, if you are integrating over a closed surface, your expression would be just this. But then you have to put circle. This means that you are integrating over a closed surface. Say, for example, if you enclose you're integrating a vector function over a closed sphere, so you will use this expression. So what's crucial about this is that what's crucial about this is that you always put the direction of the patch of area to be positive if it's outward. So it's for closed, for example, if you have a closed surface, the outward direction, of the patch is always positive. But for open surfaces, here, like this one, you can also use this as your direction of the area. But remember that you can always use different orientations, but always use your right hand to determine the direction. So if it's like a plane on the XY plane, and then your area direction would be going up. So just use your right hand. Remember that. So what does this expression mean? This means flux. So let's see what it means. We'll see what flux means. So by the way, if as an illustration, if B describes the flow of fluid, mass per unit area per unit time, then the integral V dot dA represents the total mass per unit time passing through the surface, or this is called the flux. So if you have this as the surface, this is the measure of the flow of the material out of the surface. This one, the flow of the vector function, or the fluid that is represented by the vector function out of the area. That's the flux here. That's just the measure of it. Now, the value of the surface integral depends on a particular surface chosen, but there are also vectors, as I've said earlier in here. This one are not equal. The integral in the line integral, this sorry, this one and this one, where is 10? Here. This one are and this one are not equal. But there are times that they are equal because we're using a conservative vector function. It's also the same thing as for surface integral. If we use um, the conservative vectors, then regardless of any surface that you use in integration, the closed surface integral will be zero, or meaning um, the the surface integral, whatever surface that you use, is the same. So, example, calculate the surface integral of this vector function. So in this case, you have a vector function with x component, y component, and z component. So calculate the surface integral of v, where v is 2xz x hat, x plus 2y hat, z squared minus 3z hat, over 5 sides, excluding the bottom. So you're doing the integral on this side, on this side, on this third side, on this fourth side, and on this side. The bottom is not included in the integral. So calculate the surface integral of v over 5 side, excluding the bottom of a cubical box with side of 2 units in this figure. Let the upward and outward directions be positive, as indicated by the arrows. So going up is positive, going outward is also positive. So let's look at this. So if you one take one side at a time. So let's consider this side, this side, this side here. This side, this one, this side. So on this side, x is equal to 2. X is equal to 2. And by the way, your dA, your patch of area in this side is equal to dy dz. Dy dz. Why? It's the plane, this plane is on the yz plane. The plane of the first face is on the yz plane. So your patch would be dy dzx. It's going outward, going to you, it's positive. So what is now v dot dA? So v dot dA will just be this one. Why? Because in this case, your dx would be what? Your dx would be 0. Why? Because x is equal to 2, and the derivative of x is equal to the derivative of 2, which is 0. So your dx would be 0, so that this is supposed to be dy dz, dx dy plus, I mean, dx dz y hat. There's another term here. And dx dy z hat. But the dx there is 0, so that's why you're only left with one component. You're only left with one component. So this component will be dotted to only this component, this component. Here you have 0, so 0, so everything will be 0. So v dot dA would be 2xz 2xz times dy dz. So here you have 2xz for here, and then your dy dz. Your dy dz. That's dA here. So everything, since x is equal to 2, so you can write this as 4z dy dz. And so your surface integral will be, this. So integral with respect to y and z, but in this case it's an easy integral. So you have 4 out of the integral because it's constant. So your dy will just be from 0 to 2. Your dy will be from 0 to 2. Control Z. It's from 0 to 2, and your dz will be from 0 to 2 also. So you will have an integral equal to 16. Equal to 16. So for surface number 2, here, this one, this surface, it's the same surface for, it's the same orientation for the first surface. It's the same orientation as this surface, but the direction of dA would be negative because the x, the dA here, you already set to be positive. So this one now, going to the other side would be negative. So your dx here would be negative. I mean, your dy dz here would be negative because it's in the opposite side. And the x is equal to 0 in this case. That's equal to 0. So in this case, in this plane, x is equal to 0. In this plane, x is equal to 2. So here you have that. So your VDA will be equal to this. But of course, x is equal to 0, so everything will be 0. So the integral of v dot dA is equal to 0. For y equals 2, for the third surface, for the third surface, you'll just be dealing with this surface. And this surface is oriented or is parallel to the xz plane. So naturally you will use the dx dz. So this one is dx dz. And the direction of your patch would be perpendicular to the orientation. So this is now going to y. So this is now your dA. So your v dot dA. So this is now the this is y component, and so you're just be dotting with this term. Dx, the other surface are 0, so if you dot that with this is 0, and also this with 0. So you will only have x plus 2. So x plus 2 dx dy. Remember, all the directions are gone because you have already dotted the directions. So this is a scalar function now. So you'll be integrating with you will be integrating scalar functions. So this is now x plus 2 dx from 0 to 2. The x would be from x0 to 2. And then your z is from, of course, your z is from 0 to 2 also. So here you will have this. So you can integrate this because dx and dz are independent because they're just in one plane. They're independent. So you can get 12 because the integral of this is x squared over 2 plus 2x evaluated from 0 to 2, and then you get 12. So for the fourth integral, for the fourth surface integral, for the fourth one, this one is the surface. This is the surface. Um, this is the surface, the fourth patch. But this time, it's going in this direction, going to the left. So that would be now negative. Negative dx dz y hat. So that's now negative dx dz y hat. So again, your v dot dA, this is now negative x plus 2 dx dz. And then uh, if you get the integral, you will just get negative 12. In this case, they're the same. They are, if you sum them, it's 0. In this case, for this one, it's not the same. So for the fifth surface, you consider this you consider this surface only, this one. So what is the patch of area here? The patch of area is dx dy z hat, and this is positive. Of course, if the direction is here, it's negative in that direction, but this one is positive because it's going upward. So and here you have z is equal to 2 on this plane. Z is equal to 2. So you will have this z is equal to 2, and dA is dx dy z. So your v dot dA, this one will just be dotted to the z part. Y times z squared minus 3. So this is now y times z squared minus 3 dx dy. Or what? Z squared is what? 2 squared. That's 4 minus 3 equals 1. So this is just equal to y dx dy. So the integral would be 4. So the total flux, therefore, you just add everything. You just add everything. So that's 20. This is 20, all in all. So I hope you get the essence of a line integral and of a surface integral. The next integral will be volume integral, and this will be easier compared to the first two. But I know that you already have some know-how of the first two. The volume integral is an expression of this form. It's an ordinary triple integral without direction. This is the form of that. So here is a integral of a t or a function with respect to volume, infinitesimal volume dt, or d tau, I mean. So t is a scalar function. So dt is, of course, in Cartesian coordinates, but dx, dy, dz, but in other coordinate system, as we will learn later, the d tau is different from this. But for the Cartesian coordinates, you have the d tau would just be dx, dy, dz. But if you're integrating, a vector function, this one has components. The components would be vx x hat. It has also a component vy y hat, and another component dz z hat. That would then reduce to this one, uh, these integrals. But again, each of these, each of this one is just looking like that. This one is also looking like that, and this one is also looking like that. So it's uh, uh, much simpler. And everything, the theta would just be this one, and t would just be in a function. So again, in Cartesian coordinates, the x hat, you can take this out. You can also take this out. You can also take this out because they are constants. You can take them out in the integral. So let's go to the example immediately. Calculate the volume integral of this vector, or this scalar function xyz square over the prism, this prism here drawn in the figure. So it has, the x has limit from 0 to 1, and the y has limit 0 to 1 also, and the z has a limit from 0 to 3. Those are the limits of the integration. So now, what is this line? What is the function that represents this line? This line represents a function x equal to y. This one here. It's a line. The curve is a line. And this line is represented by x equal to y. You can get this. You can get this line equation of a line by using intercepts. In algebra, you can get the equation of a line. So here, Control Z. So t is equal to xyz square. So you have you can, this one is already separated, no? Z square y and x. Z square y and x. But in this case, the solution is they get the integral of x first with respect to dx. This is the deta of dx, dy, and dz. And then after getting the integral of x, they integrate with the y. Because why is that? Because x and y are independent of each other. Because of this line, they're independent of each other. So first you integrate the x, but the x has limits 0 to 1 minus y. This is because of this line. Because of this line. So the limit is from 0 to 1 minus y. So for example, y is 0, x would be equal to 1. If y is equal to 1, then x would be 0. So that's why this is the limit. And also, for y, so if you integrate this, it would be x squared over 2. But you have to evaluate from 1 minus y to 0. And then again, you integrate this. Sorry. So integrate this, and then you will get this integral. By the way, the y and z are now independent of each other. There's no line connecting z and y, so they're independent of each other. So you can write the integral to be like this. To be like this. So that's the result of that. So I hope you can see why it's 3 over 8. So you can integrate this Um, z cube over 3, so this one would be just y square over 2 minus y cube over 3. And these are the limits of integration 0 to 1, and then you have 0 to 3. So please review the examples and understand them. Next meeting will be starting with fundamental theorem of calculus. So what I want you to do as an activity for you at home, you can rewrite by hand the examples and then learn. And if you don't understand, you can ask me in our Google room or in our Molia room. I will also post this video for you to review them. And that's basically, if you understand all these kind of integral, then you would be able to solve electrodynamics problems in the future. In the future lectures, it will be easy for you to understand. So uh, that's all for this session. So in the next meeting, please interact with me. I'm planning to put up an interaction session with all of you uh, in chapter 2. So when we solve electrostatic problems, um, we have a YouTube live discussion, and then we have a following interaction at Zoom or in Google Meet for clarifications. So we'll just be doing the lectures for an hour, and then the interaction will be 15 minutes right after. So thank you so much for listening, and I hope you learned even a little bit. That's okay. Don't pressure yourself because this thing is kind of new to us. So um, just um, learn. Uh, someone asked me when that would be in chapter 2. So we're still in chapter 1. We're still reviewing some mathematical rules. So um, in chapter 2, we will have an interaction session. And then also in chapter 2, we will be doing problems. I will give you problem sets from time to time. And so by that time, you will be doing many things in your home. But don't pressure yourself. Just study. Just review the lectures, because sometimes in the interaction session, I will be asking you some questions. So if uh, you can answer, then I will give you some plus points, because that's for now, that is the way of evaluating the students. So please tell your classmates to attend always our lectures, because it's important to know the informations, the discussions firsthand. So that's all for today, and I hope you'll have a nice day ahead. See you next meeting.